So I'm going to do quickly the moment. Okay, so I'm going to squeeze in if I can. Right, so we're going to take moment again. Right, and take undo. So I'm going to take a moment. Right, so we're going to take moment anti-clockwise. Summation about moment at any position in the z-axis. Any position x is equal to 0. So we will have clockwise anti-clockwise, so 3000 x squared, right? Then plus by moment evenly distributed load as a function of x. So moment evenly distributed load as a function of x is equal to minus 3000 x squared. Okay, 3000 x squared. Then from here, I'm going to squeeze, right? So if I'm going to take moment, z anywhere at point x is equal to 0. So on the gradient distributed load, this will be equal to minus. Sorry, this will be equal to positive 1000 x squared over 2. So sorry, x squared, and then the distance will be x over 3, right? Then plus by moment gradient distributed load as a function of x, the whole thing is equal to 0. Okay. So from here, moment gradient okay, so the moment for the gradient of the gradient distributed load will be equal to minus 1000 x cubed over 3. Okay, then if we do summation of both of them, so this will be equal to minus 1000 x cubed over 3, and then we have minus 3000. Okay, we get minus 3000 x squared. Okay, so if you look at this equation over here that I'm going to highlight in blue, right? This equation over here that I'm highlighting in blue, and if you look at the distributed load, okay, the equation that I'm highlighting in blue is exactly the same. Okay, so you can see for yourself, right, how much more steps is needed. Okay, how much more steps is needed, right? Now, to use the positive shear and positive bending moment, we are lucky that point A has no what? Support. If point A has support, you have to find the what? The reaction at point A. For this case, we managed to don't need to do that. Okay. So now, this is a very interesting problem. Now, so the thing now is this, in terms of this topic, if we change, what if now? Okay, so we're gonna do something different, not different. What if now? Okay, what if now? Okay, we have a load now. Same thing. Okay, our distributed load is the same, right? So now our distributed load is the same. So let me highlight what we had before. Okay, so now the one that we have just completed, we have this sort of distribution, right? So this is 6,000, right? This is 18,000, right? So we have a cantilever beam. When x is equal to 0, x is equal to 6, we have V, M, theta y, right? So let me write properly. I will not rush. So we have v m y, right? So we know that this is 0, right? And then we also know that this is equal to 0. Whereas this case, we only know this is 0, okay? So 1n is cantilever, so I better draw this cantilever more obvious, okay? Now, what if now we decided to change the holding, okay? So now, what do I mean by that? What if now, okay, we have taken the entire same load, same loading system, okay, same loading system, wait. Now, we don't have a cantilever beam. Okay, so this is our distribution now. Distribution did not change. I highlight again, the distribution did not change, okay? So this is x is equal to 0, right? Now this is x is equal to 6. Now it is what? Simply what? Simply supported, okay? So when it's simply supported, what will happen? So you have v m theta y. You have v m theta y. So what is going to see different is this, okay? What is going to see different is, let me draw a line in the center so that you know that there are two separate configurations. Now what you see different is this. V at point A, or V at x is equal to 0, right? So this is x is equal to 0. The other one is x equal to 6, right? Right. So for the simply supported beam is different from the cantilever beam in terms of boundary condition, right? So over here, right, where it's simply supported, the one on your right, V is no more equal to 0, right? Because there are reaction forces already, right? You know that at one end, or I call it point A, where x equal to 0, B is where x equals 6. We know that there is reaction at point A, at point B. Whereas at a cantilever beam, at point A, the shear force is equal to 0, right? So now, condition changes. The moment at point A now is equal to 0, like what I told you all before, is because when you remove the support at B, the structure rotates. Now the moment at point B is also equal to what? 0. Right? So you see the boundary condition changes already. When the boundary condition change, right, the unique solution also change. Okay, so let me show you what do I mean by that. Okay, so now the equation of the distributed load did not change at all. So now we still have omega as a function of x is still equal to 2000x plus by 6000. Right? Okay, so now, as I said, the load distribution did not change for both cases. Okay, so you still apply dv by dx is equal to minus omega as a function of x, and then this will be equal to minus 2000x minus by 6000, right? Then you integrate the first time, v as a function of x is equal to minus 1000 x squared, right? Minus 6000 x plus by c1. Okay, I'm going to call this my equation 4. Now, can we solve for c1? Anyone at this stage? Hello? Anyone? Can you hear me? Hello?
Yes.
Okay.
Yes.
Yes, right. You guys are watching a football somewhere else or watching a game that I don't know or what. Okay. So for this case, can you find C1 now? The answer is no. You cannot find C1 because your shear force V at x is equal to 0 is not equal to 0. So you don't know what is it. When x equal to 6, V is also not equal to 0. What is it? You also don't know. Okay, so all these two, when you don't know that it's not, when it's not equal to 0, you don't know what they are. So when this is the case, you move on. You can see how the solution change with boundary condition now. Okay, the thing now is this: you have to trust the math. Okay, I know it's not easy to trust the math. It took me a long time to trust the math, but I want to tell you this: trust the math. Okay, so now we have m, we integrate again. Now we have m as a function of x. So now this is minus what? Minus 1000 x cubed over 3 minus by 3000 x squared plus by c1x plus by c2, equation number 5. So now we know our boundary condition for the moment. Yes or no? We are aware. So we're going to substitute when x is equal to 0, moment is also 0 into equation number 5. Okay, right, into equation number 5 now. So what we get now, right? So we're going to substitute equation number 5. So what we got now, so when we substitute, we realize that C2 is equal to 0, right? We did that. So therefore, m as a function of x is equal to minus 1000 x cubed over 3 minus by 3000 x squared plus by c1x. This is your equation 5a. Because we found from our first boundary condition, when x is equal to 0, right? M is equal to 0. We realize that C2 is also equal to 0. Okay, so next we're going to substitute when x is equal to 6, M is equal to 0 into equation 5a. Right? So you will have 0. So this will be equal to 6 power 3. Come on, turn on. 6 power 3 times by 6 power 3 times by 1000 divided by 3 is equal to minus 72,000 minus by 6 times 6 times by 3000 minus 108 plus by 6c1. So c1 is equal to 10812 108 plus by 2 divided by 6 is equal to 30,000. Okay. So therefore, right? Therefore, m as a function of x is equal to minus 1000 x cubed over 3 minus by 3000 x squared plus by 30 times 10 to the power 3 x. Okay, so this is your equation 5b now. And then your shear force equation will be equal to minus 1000 x squared, right? And then minus by 6000x plus by 30 times 10 to the power 3. So this is now your equation 4a. Okay, so this is just by using the integration method. As I said, you have to trust the math. If you don't use the integration method, you use the superpositioning method now, right? Let's say you decide to use, I'm not going to show you that, but you can try. If you're going to use the superpositioning method, it will be very, very much longer. Why? Why will it be much longer? If you decide to use, okay, I put down here, using superpositioning method. Okay, using superpositioning method. The problem is this: must find the reaction at point A. Right? You have to solve the reaction at point A first. Then you can then you can solve the what? Then you can use the the equation where we started from left to right, because you need to know what is going on at point A. Okay, so it's a longer method. So I find this method, it took me quite a while to get used to it. I'll tell you that.